the entire class back together and assemble all of their results so that everybody can see them. So if you can put them all up on the board, that's a really useful thing. And that's especially useful when you're talking about difference equations and calculating example trajectories, because then you can get a lot of different kinds of trajectories without having every student have to go through all of the different possibilities. Okay, so part 3, we introduce the idea of boundedness. And I think this is one of the more sophisticated ideas that gets introduced in this lecture. And I think you'll probably end up spending a lot of time helping students develop intuition on the idea of boundedness. So often I find it helpful to phrase kind of boundedness in the following way. If a trajectory is unbounded, then it's not possible to find any single number such that the absolute value of the trajectory is always less than that number. So if you can find such a number, even if it's a really big number, even if it's 100 million, if you can find a number such that the absolute value of the trajectory is always less than that number, then it's bounded. And you'll come up with all sorts of different ways of explaining what a bounded trajectory is versus an unbounded trajectory. A useful tool to use in the classroom is to encourage your students to challenge each other. So present a difference equation and an initial condition. Look at what the trajectory, calculate a few points of it, and then ask the class, is this bounded or unbounded? Often they'll have an intuitive answer. Well, it looks like it's blowing up or it looks like it's not. But see if you can get them to use the mathematical language. Ask them to prove it to you. Find me, if you argue that it's bounded, find me a number that the absolute value is always smaller than. If you argue that it's unbounded, tell me why. Another issue that often confuses students is when a trajectory is bounded, a number that serves as a bound for that trajectory is not unique. So, for example, if the absolute value of a trajectory is always less than 2, well, then the absolute value is always less than 3 as well. So students often find it difficult to kind of handle this non-uniqueness in terms of boundedness. So that's something you may have to discuss explicitly in your class. Okay. In part 4, we add a twist to the material we've done so far. We allow our difference equations to take on complex values. So maybe we give them complex initial conditions, or the difference equations themselves have a complex number in them. None of the mechanics are any different, but it requires them to use complex arithmetic. And depending on how comfortable your students are with complex arithmetic, this can be more or less difficult. This is another one of those topics that will just require time and practice. So having extra examples and allowing enough time for students to work through those examples can be really important to helping them feel comfortable with the idea of complex trajectories. Now, in order to evaluate whether or not a complex trajectory is bounded, students need to be able to take the absolute value of a complex number. And this is a topic that is addressed in the tutorial, but if you discuss complex arithmetic in your class outside of the tutorial, make sure that students know how to find the absolute value of a complex number in order for them to be able to work through this section. So part 5 introduces the mandelbrot set. And in some ways, this is conceptually the most lovely part of this entire lecture. At this point, students need to feel comfortable with deciding whether or not a trajectory, a complex one, is bounded or unbounded, because that's the way that you define what points are in the mandelbrot set or not. But hopefully, by this point, all of the hard work and heavy lifting has been done by your students in terms of the mechanics and kind of intuition building on trajectories. And they can kind of just enjoy the beautiful results that come out. So at the end of this section, we ask the students to guess what the mandelbrot set is going to look like. And this is one of those times where you don't need to spend too much time in class on having students brainstorm and then coming back together with their suggestions, because the answer is so strange and seemingly unpredictable that it's really more a thought exercise at this point, and they're kind of waiting to see what the final answer is going to be. So the very last section is on fractals in general. And it really is just a very brief introduction to some beautiful images that will hopefully inspire your students to pursue some of the extensions that we were talking about earlier and to do future work in this field. At the very end, we also return to the chaos game and the Sierpinski triangle. And as I mentioned earlier, we present the brief computer simulation that shows you kind of the very surprising and interesting pattern that the chaos game will result in. And so I hope by the end of this lesson, your class has learned an extraordinary amount of new material, most material that students in high school never get a chance to see, and that all of you have kind of become interested in a brand new topic that could take you in all sorts of directions in algebra and geometry and beyond. So thank you very much for your interest in this lesson. I really hope you enjoy making this lesson on fractals exciting and interesting to your class, and I wish you the best of luck.